Good evening to all of you, the participants, and thank you, Dr. Yadav, for giving me opportunity to speak on, I think, the whole workshop. So today, the second day of the workshop. Actually, this is, I think, this is second day.
Yes,
So I
it,
think,
it is not day three.
okay, 1 minute,
One
wait a
is
minute.
asking day three. No, it's a day one, day two actually.
Actually, it is day 2, not day 3.
Yes. So don't worry, sir. We
No,
can
no,
continue.
no. I have. Hmm,
Day two. Actually,
wait a minute. I am just sharing. Either the expression was not purely corrected, and later it was corrected by the Professor R.A. Fisher, who is known as father of modern statistics. So now we'll be discussing. So this was the story behind the name T test or student T test. Now, actually, we studied two types of distributions. One is theoretical distribution and another one is sampling distribution. So this T comes into the category of sampling distribution. So sampling distribution is nothing but it is the distribution of the statistic, that is function of the sample values, while the theoretical distribution is concerned with the distribution of the random variable under consideration. So because random variable has variation in its values, that's why there is a distribution. And we also know that the value of the statistic vary from sample to sample. So if we see that there is a variation in the values of the samples, if you are getting all possible samples, you can see the variation, the values of the statistics are different. So there is a variation in the values of the statistic. That is why it must have some distribution, and that distribution is known as sampling distribution. And in the category of sampling distribution, we basically there are four distributions: TF, chi-square, and Z distribution. Z is considered as large sampling distribution, or also known as approximate sampling distribution, while TF and chi-square distributions are considered into the category of small sampling distribution or exact sampling distribution, where the sample is less than or equal to 30. Because sample less than or equal to 30, sample of size less than or equal to 30 is considered to be small, while greater than 30 it is supposed to be large. So we'll be discussing different T applications of the T distribution, that is sampling distribution of the statistic. So statistic is nothing but it is function of sample values. So sample mean, sample variance, sample coefficient of variation, sample correlation coefficient, these all are the statistics. So we'll see which statistic we are using in testing of hypothesis, and accordingly we will find the distribution of that statistic, and we'll see if the sample size is small. So all of the sampling, all of the statistics have their distribution either T or F or chi-square. So now today we'll be discussing the different applications of T statistic or T distribution. So one sample t-test where we wish to know the significance of the mean. That is, if we wish to know the average marks of a class is 67 or say 70, or we wish to know the average height of the student is 5.6 inch, say 5.5 inch, or in say medical sciences we know, we wish to know the average heart rate is 72, or we wish to know that the upper upper limit of that, I mean, blood pressure is the average is say 122 or say 125. So if you wish to check that one, then you have to take a sample, and accordingly we will calculate the statistic and we'll get its sampling distribution, and we get its standard error, and then we will standardize it, and then we'll see the distribution of that statistic. So that statistic will follow either t distribution or chi-square distribution or f distribution in case of small sampling distribution. So today we will be discussing only the applications of t distribution. So here we are interested in knowing the significance of mean. That is, we wish to know that a group of population is having a particular mean, say mu. So there are some assumptions we'll be discussing which are mandatory for these tests to perform better, whether large sampling distribution or small sampling distribution. We'll be discussing there are basically 2-3 assumptions which are I mean fulfilled by all these test sampling distributions. That is the observation. First one is the parent population should be normally distributed. That is the population from which you are doing sampling or you are getting the sample must follow normal distribution. The second one is the observations must be independent. That is, sample should be random. And in case of t distribution, there is two more assumptions, that sample should be small and variance should be unknown. These are the 4 assumptions for the t distribution to perform well. So now we'll discuss one by one. So one sample t-test determine whether the sample mean is statistically different from a known or hypothesized mean, population mean. That is, we want to check the null hypothesis H naught says that mu is equal to mu 0 or mu naught, particular this hypothesized population mean. The one sample t-test is a parametric test. This test is also known as single sample t-test. The variable used in this test is known as test variable. There is a basic difference between statistic and test statistic. Just now, I think in next slide we will be discussing. So in one sample t-test, the test variable is compared against a test value, that is this hypothetical value, which is a known or hypothesized value of the mean in the population, that is population mean. Where we use this test, so the one sample t-test is commonly used to test the following: statistical difference between a sample mean and a known or hypothesized value of the mean in the population. That is, whether it is significantly different from the population mean or it is just representing that population mean. Statistical difference between the sample mean and the sample midpoint of the test variable, that is also supposed to be hypothesized mean. Statistical difference between the sample mean of the test variable and chance. This approach involves first calculating the chance level on the test variable. That is, we calculate the standard error of the sampling distribution of the statistic. The chance level is then used as the test value against which the sample mean of the test variable is compared. So first we wish to know what is the hypothetical value, that is chance value, or we are saying the chance level of the test variable, that is hypothesized mean. And then we'll take a sample from that population and we'll calculate the corresponding statistic and we'll compare the two. Statistical difference between the chance score and 0. This approach involves creating a change score and 0. Whether you have changed the scores and just we are comparing with the origin or say 0. Change score from 2 variables and then comparing the mean change score to 0. which will indicate whether any change occurred between the two time points for the original measure. What we do in pair t-test, if the mean change score is not significantly different from zero, no significant change occur. If we wish to know the I mean effectiveness of a say drug, so we check the particular thing. Suppose we wish to know the whether insulin is effective in reducing glucose level or not, so we'll check the glucose level of the patients uh, of some size, say sample say 10. Then after giving insulin, injecting the insulin, then we'll check the glucose level and then we will perform the pair t test. So this difference difference should be zero, so the null hypothesis will be d is equal to zero, that the difference is zero. It means the drug is not effective at all, and we will see the significance of that. Note, the one sample t-test can only compare a single sample mean to a specified constant, that is hypothesized population mean. It cannot compare sample means between two or more groups. It cannot compare more than two groups. Oh, sorry. It is for only single group. And if we wish to compare the means of the two group, then we will go for the independent sample two sample t-test. And if we wish to further check the equality of means of more than two groups, then we will go for the ANOVA. If you wish to compare the means of multiple groups of each to each other, you will likely want to run an independent sample t-test to compare the means of two groups, see here, or a one-way ANOVA to compare the means of two or more groups. If we are using ANOVA for two groups, then it reduces to independent sample two sample t-test. Now, what is the requirement of the data to perform this test? Your data must meet the following requirements. The test variable that is continuous, that is it must be measured on either interval scale or ratio scale. So someone was asking yesterday, what are the measures of scale? So basically there are four measure of, basically there are two measurements, say that is scale measurement and categorical variable measure, the qualitative measure, and this is quantitative, and quantitative is measured through either through interval or ratio scale, and qualitative data or categorical data is measured through nominal scale or ordinal scale. And we have yesterday we have discussed what is nominal and ordinal. Now here interval and ratio scale. So the numerical values will be interval and ratio values, and that is numerical measurement. But there is a minute difference between the two. Ratio is nothing but this is the numerical values or the ratio values, and there is a difference between interval and ratio scale is that if zero is having absolute value, absolute meaning, then it is the ratio scale, otherwise it is interval scale. So that is why the temperature is measured on the interval scale, not on the ratio scale, because zero is not having absolute meaning in case of temperature, because zero temperature does not mean that there is no temperature. Zero temperature means, it does not mean that there is no temperature. So the zero temperature means we will feel some temperature. So that is why in this, I mean, temperature is measured on the interval scale, because here zero is not having absolute meaning. Second one is scores on the test variable are independent. These are the assumptions for the t-test. So test variable must be continuous. The test variable observations are independent, that is independence of the observations. There is no relationship between scores on the test variable. Violation of this assumption will yield an inaccurate p-value. That is why observation must be independent to perform the statistical test very well. Otherwise, this p-value will be I mean disturbed. Random sample of data from the population. Random means this, that the observations are independent and the observations must follow normal distribution. They must come from the normally distributed population. So normal distribution approximately of the sample and population on the test variable. Non-normal population distributions, especially those that are thick-tailed or heavily skewed, considerably reduce the power of the test. That is why we seek some alternative tests and which are known as non-parametric tests. We will be discussing later. Among moderate or large samples, a violation of normality may still yield accurate p-value. It means if we are just increasing the size of the sample, then we can have some accurate p-value. So homogeneity of variances, that is variances approximately equal in both the samples and population. So homogeneity is important, that the variation among the values of the sample is same, is equal to that of the variation among the values of the population, and there must be no outlier or extreme values. So this is a hypothesis. So there are two types of hypothesis: null hypothesis and alternative hypothesis. Null hypothesis is nothing but it is the hypothesis to be tested is known as null, and according to Professor R. A. Fisher, possibly rejected hypothesis is known as null. And this alternative to this hypothesis is known as alternative hypothesis. Now these two hypotheses are further of two types. They may be simple and they may be composite. So if the hypothesis, the parameter of the population, or hypothesis is perfectly specified by the parameter, or the parameter is, if the population parameter is completely specified, then it is simple, otherwise it is not simple. So see here, in case this mu is equal to x bar, this is completely specified that mu is equal to this equal to mu bar. But here this is not completely specified, because mu is not equal to x bar means it may be greater than x bar and it may be less than x bar, but only it is not equal to x bar. So this will be the composite hypothesis. So here we have to test h naught such that mu is equal to mu 0, and see here, single tailed and one tailed and two tailed test depends on this composite or alternative hypothesis, and which is composite or simple. If you are taking just mu is equal to say x1 bar, then it is simple. And if you are taking here, if you wish to test that mu is greater than x bar, then this is right tailed test, right tailed. And if it is less than x bar, it is left tailed. And if it is not equal to x bar, then it is two tailed. So the critical region will lie on either side of the distribution, where mu is a constant proposed for the population mean and x bar is the sample mean. So this is actually statistic used to test the significance of the mean. This is sample mean, this is population mean, and assumed mean, say assumed mean, and this is standard error of this x bar. So one thing I would like to add here, that when W.S. Gossett, our student, formed this statistic, he wrote only x bar minus mu upon s, not sx, not sx bar. That is, he only written here s, and later Professor R. A. Fisher corrected is that this must be the standard deviation of this sampling statistic. This must be standard deviation of the sampling distribution of this statistic, not of the random variable, because you are here you are taking this statistic as a random variable. So here there must be standard error rather than the standard deviation. So it was corrected to s upon square root of n. And we know that mu is population mean, x bar is sample mean, n is sample size, and s is sample standard deviation, and Sx bar is estimated standard error of the mean, that is S upon square root of n. The calculated t value is then compared to the critical value, which is also known as tabulated value, from the t distribution table with degrees of freedom n minus 1 and chosen confidence level, that is alpha, that is 1 minus alpha 100%, that is 5%. If the calculated value is greater than the tabulated value or critical value, then we reject the null hypothesis. That is, the test will be significant. So the p value will be less than 0.05. Whenever the calculated value is greater than the tabulated value, which is also known as the critical value, then we will reject the null hypothesis, and accordingly p value will be less than 0.05. So this is data setup. I think anyone wish to know something? He or she is drawing the lines.
Dr. Anwar, you are requested not to mix in these things, otherwise you will be removed. Please, sir, continue.
Okay, thank you. So data setup, your data should include one continuous, we have discussed already, one continuous numerical variable represented in column that will be used in the analysis. The variable's measurement level should be defined as scale. In the variable view window, we will see it in hands-on session. So run one sample t-test. To run that in SPSS, so we have to click on analyze, then compare means, and in compare means we will select one sample t-test. And these are just this is I mean demo to perform one sample t-test on SPSS. So we can see here this dialog box will be opened there, and you just put here the test variable and put here the test value, that is assumed mean, and go to options and then click OK. You will get the you will get the value of the t statistic. So you just click on analyze, compare mean, one sample t-test, move to the variable. Say if you are taking this height as the main variable, and you are just want to test with whether the average height of that population is 66.5, and then you just click on OK. So that this way table will be displayed. Here you can see one sample statistic. The main variable was height, number of persons or number of units were 408, and the mean was 68.0318. Standard deviation of this sampling distribution of this mean is this. That is, standard deviation is related with the population, and the standard error of mean is this 0.26366. So this standard deviation is of the population values, and this standard error is the standard deviation of the sampling distribution of the statistic, and statistic here is mean. So this is actually main table, one sample t-test. So you can see here these are some values. We'll explain one by one: A, B, C, D, E, and F. So A is nothing but test value, which is fixed by the investigator, and this is t value, the value of the statistic. That is, this is the calculated value, and this is degree of freedom n minus 1, that is 408 minus 1, and this is two-tailed. It means we are testing that the average height is not equal. Alternative hypothesis is that average height is not equal to 66.5. So this is two-tailed, and here we can see that the p value is less than 0.05. So the test is significant. It means the average height of that is, it means the population mean, or say average height of that group is not actually 66.5. The hypothesis will be rejected at the p value is less than 0.05. This is the mean difference, and this is upper and lower limit of the confidence interval for that statistic actually. These are that values actually we have discussed so far. And obviously we see that if you are comparing the tabulated value with the calculated value, then you have to see that value. Either you can calculate that value from the Excel sheet, or you can see that value from the t-test table. Otherwise you see the p value which is given in almost all softwares. You can take decision according to the value of this p value. So here we can see that the value of p is less than 0.05, so we will reject the hypothesis. So here there is a significant difference in mean height between the sample and the overall adult population. That is, p is less than 0.001. It is 1%, but it is 0.05, less than 0.05. So if you are taking 5% level of significance, if you are taking 1%, it is 0.1%. It is testing with the 0.1% level of significance. So the average height of the sample is about 1.5 inch taller than the overall adult population average which we have taken. You can see from here. See 66. This is 66.5 and the value is 68.0135. That sample mean. And population mean is this 66. So you can see the difference is almost 1.5 inch. Now moving one step ahead towards the independent sample, two independent sample t-tests. The assumptions are same, but here we are considering two samples coming from two different populations. So we wish to know that the mean of the two populations are same, or otherwise you can say in either way, in other way, that they are coming from the same population. The samples are coming from the same population. So the independent sample t-test compares the mean of two independent groups in order to determine whether there is a statistical evidence that the associated population means are significantly different. The independent sample t-test is a parametric test, definitely, and this test is also known as independent t-test, independent measure t-test, independent two sample t-test, student t-test, two sample t-test, uncorrelated score t-test, unpaired t-test, unrelated t-test. These all are the names of this independent samples t-test. So one more assumption is taken here, that the variance of both the populations should be same. That is, there must be homogeneity of the variance. But if there is not homogeneity in the variation, then even then we can perform this test, and we will see through Levene's test. So the variable used in this test are known as dependent variable or test variable, and independent variable, or this is also known as grouping variable, which is taken in the form of category. That is, this grouping variable is qualitative and the test variable is quantitative, or it is measured on the scale measurement. So these are the common usage. Independent sample t-test is commonly used to test the following: statistical difference between the means of the two groups, statistical difference between the means of the two interventions, statistical difference between the means of two change scores. So you can compare the two techniques. You can compare the independence of the average of the two techniques, or to say interventions and change scores. So the independent sample t-test can only compare the means of two and only two groups. It cannot make comparisons among more than two groups. If you wish to compare the means across more than two groups, you will likely want to run a ANOVA, that is known as one-way ANOVA. If you wish to compare the means of more than two groups. So that data requirement is same. The variable must be continuous. dependent variable and independent variable should be categorical, and the observations must be independent, and sample must be random. There is no relationship between the subjects in each sample, that is observations are independent. This means that subjects in the first group cannot also be in the second group. You cannot take a common observation in both the samples. So no subject is in either group can influence subjects in the other group. No group can influence the other group. Violation of this assumption will yield an inaccurate p-value, which we have discussed earlier. Random sample of the data from the population, we have already discussed that the observation must be independent, and the observation must be normally distributed, and there must be homogeneity in the variance, and obviously there must be no outliers. Note, when one or more of the assumptions for the independent sample t-test are not met, you may want to run the non-parametric test, and we should know that the equivalent test to this independent sample t-test is Mann-Whitney test. If the normality assumption is not met, then we seek for the equivalent non-parametric test, and the equivalent non-parametric test is Mann-Whitney test. Researchers often follow several rules of thumb. Each group should have at least 6 subjects, we have discussed. If you are dealing with 6 or lesser observations, then we should go for the non-parametrics, ideally more. So inferences for the population will be more tenuous with too few subjects. If you are dealing with very few subjects, then parametric test will perform, inferior to that of the non-parametric test. So a balanced design, the same number of subjects in each group, that will be known as balanced design. If you are dealing with the n1 and n2 observation, this is n1 in one group and n2 in another group, then this is unbalanced design. Is ideal. Extremely unbalanced design increase the possibility that violating any of the requirement or assumptions will threaten the validity of the independent sample t-test. If you are taking, just say, one group is 10 and another one is 100, so you will face some problem. The p-value will be affected ultimately. And the hypothesis, as we know that we are testing the equality of two means. So this is mu1 is equal to mu2. This is a null hypothesis, and the alternative will be, if you are dealing with that, if you wish to study, two-tailed, if you wish to perform two-tailed alternative hypothesis, then this is mu1 is not equal to mu2. Otherwise, if right-tailed, then mu1 will be greater than mu2, and left-tailed mu1 is less than mu2, or the equivalent is this. Levene's test for the equality of variances. As we have discussed that there must be one assumptions followed by the two populations, is that the equality of the variances between the two populations. So that is also known as homogeneity of the variance between the populations under consideration. So recall that the independent sample t test require the assumption of homogeneity of variance, that is both groups have the same variance. SPSS conveniently includes a test for the homogeneity of variance called Levene's test whenever you run an independent sample t test. The hypothesis is that the sigma 1 square, that is variance of first population, is equal to variance of the second population, and the alternative is that both are not equal. So this implies that if we reject the null hypothesis, this one, that is if the variances of both the populations are not equal, even then we can perform t-test. Now, Levene's test, it suggests that the variance of the two groups are not equal, that is the homogeneity of variance assumption is violated. The output in the independent sample t-test table include two rows: equal variance assumed and equal variance not assumed. So if you have seen that equal variance is not assumed, you see through the Levene's test, if your hypothesis is rejected, then you have to see the value corresponding to the this assumption that equal variance not assumed. If Levene test include that the variances are equal across the two groups, that is p value large, you will rely on the first row of the output, that is both the populations are having a equal variance assumed. When you look at the result for the actual independent sample t test under the heading t test for equality of means, if Levene's test indicate that the variances are not equal across the two groups, that is p value is small, that is less than 0.05, you will need to rely on the second row of output, equal variances not assumed, when you look at the results of the independent sample t test under the heading t test for equality of means, and we will see it while doing hands-on on spaces. The difference between these two rows of outputs lies in the way the independent sample t test statistic is calculated. When equal, so there is some formula for the statistic is different for equal variance and unequal variance, we'll see. When equal variances are assumed, the calculation uses pooled variances, and when equal variances not assumed, the calculation utilizes unpooled variances and the correlation to the degrees of freedom. And the correction, definitely we'll then correct to the degree of freedom, n1 plus n2 minus 2, and this way we'll correct this will be for the pooled, and we'll correct this degrees of freedom for if we are dealing with the unpooled variances, not equal variances. So the test statistic is nothing but the statistic under the null hypothesis is known as test statistic, otherwise it is statistic. So see here, equal variances assumed, then the statistic is this, and SP is nothing but it is pooled variance. This is this way we pool it, n1 minus 1 s1 square plus n2 minus 1 s2 square upon n1 plus n2 minus 2. And this is the test statistic x1 bar minus x2 bar upon SP square root of 1 upon n1 plus 1 upon n2. And these we know that this is mean of the first sample, mean of the second sample, sample size of first sample and sample size of second sample, and this is standard deviation of the first sample, standard deviation of the second sample, and this is pooled standard deviation. And here you can see the degree of freedom will be n1 plus n2 minus 2, and 2 will be actually degree of freedom is nothing but it is number of observations minus independent observations minus number of linear constants. So here one constant one constant is taken that the sum of the observation and divided by the number is equal to the mean. So one degree of freedom is left here, and one while calculating s1 square and s2 square, one for x1 bar and one for x2 bar. So that is why here n1 plus n2 minus 2. So there are two linear constants. So total number of independent observations are n1 plus n2 and two constants, so minus 2. So then note that this form of the independent sample statistic assume equal variances, and because we assume equal population variance, it is okay to pool the sample variances. However, if this assumption is violated, the pooled variance estimate may not be accurate, which would affect the accuracy of our test statistic, that is which we are using, that is t statistic, and that will rely on the p value, that will depend on the p value. So the if we have assumed that equal variances are not there in the two population, so we'll take this statistic x1 bar minus x2 bar upon s1 square upon n1 plus s2 square upon n2. Independent variances of this is sample variance for the first sample, and this is sample variance for the second sample, and we'll see the correction into the degree of freedom. So this is the formula for the correction of the degree of freedom, and this way we will calculate the corrected degree of freedom this by this formula. Data setup, we know that we will set the observations in one column, and the another column, in another column we will put the categorical values, and we'll code the both the groups, one group by 1 and another group by 2, and we have this way we have 2 column, and we'll see in SPSS. So to run the two sample independent t-test, we will click on analyze, then compare means, and go to independent sample t-test. So this dialog box will be opened, and you just put here the test variable, and grouping variable will be dragged in this grouping variable, and then click. You have to define groups, one for first group and second for second group, and then click OK. You will get the analysis of the data. These are the things which we have discussed just. So here you have to define the groups. You just put 1 here and 2 here, and click on continue, and then you will get the analysis of the data. Say this is data, and this is actually we have to check definitely before performing these parametric tests. We have to check the normality of the data. So to check the normality, we will go for the either for the box plot, or we will go for the two tests yesterday we talked about, and these two tests are Kolmogorov-Smirnov test and Shapiro-Wilk test, to see the normality of the data. So running the test, we will run through this analyze, compare means, independent sample t-test, and we'll have the descriptive in this way, and this will be basically the independent sample t-test table. Here you can see, here we have the interpretation is very important. You see here, while performing independent sample t-test, SPSS automatically perform this Levene's test for the equality of the variance. So see here, there are two options which we have discussed, that equal variances assumed and equal variances not assumed. So see here, the value of the F statistic is this, and the significant value is 0.000. It means it is less than 0.05. So we will reject the null hypothesis. It means there is not equality in the variances of the two populations. So we will go with this option, that equal variance not assumed. So we'll see consider the t value as this value, not this. If this value, if this would be the value greater than 0.05, then we'll consider this value, and if it is less than 0.05, we'll consider this value, because equal variances are not assumed there in the population. So see here, this is a value of the statistic, and corresponding to this, the p value is this 0.000. It means the null hypothesis will be rejected because it is significant. It means the means of the two populations are not equal. They differ significantly.
Sorry to interrupt you, sir. Hello.
Yeah.
Sir, please, actually many participants want that please give some real life examples related with this these tests.
Definitely we'll be discussing while doing hands-on on SPSS, and definitely we'll talk about some more examples.
Okay.
So if definitely if you here wish to know the see if you wish to know the real life example, you can consider from the class. If you wish to know the average marks of one class and average marks of the another class, or if you wish to know the average income of one group and average income of the another group, and if you are taking some health parameter, say any parameter you are considering, then you are taking two groups of the people, and you are considering that you are taking measurement on that particular parameter, maybe health parameter, and you see whether the average of that group. See, if you have two groups of population and you wish to know the glucose level of that persons, and you wish to check that whether both the group are having equal average glucose level or not, then you can perform this independent t sample t test. So there are so many examples when you are comparing just two populations, and you are calculating their means. It may be economic, so you, if you are comparing the, you can compare average sale of two, I mean, say two cities for a product, you can see. So you can, this way you can calculate. There are so many examples. It is up to you where, but you see just what is your purpose. You are just going to compare the average population mean of two populations, whether they are equal or not. If you wish to know the average sale of the particular product in Lucknow is equal to the average product, average sale of that product in Kanpur, there you can perform independent sample t test. And obviously decision is making on the basis of the p value. If your p value is less than 0.05, then we reject the hypothesis. Otherwise we are not in a state to reject that hypothesis. Now pair t test, which is basically very much applied in medical sciences. If you wish to know the effectiveness of a treatment, or effective of a drug, of effectiveness of a, say, technique. If you are in teaching, if you are dealing with you have you just wish to know some technique, you have I mean evolved some new technique, and you wish to know whether this technique is effective to increase the IQ level of the students, then you can perform this pair t test. You just see group, check their IQ level, and then perform your technique, and then see the IQ level of the students. And one we have talked about in medical sciences, that if you wish to know the effectiveness of, say, insulin, then you take the glucose level before giving insulin to the patients, or say group, and then see the after injecting that insulin, and take the observations of the glucose level, and you see the difference between the two. Here it paired, it is known as paired sample because there is only one group, and we take the repeated samples, repeated observations. So two times observations are repeated, before and after. So this way you can perform this pair t test. The pair t test compare two means that are from the same individual object or related units. The two means can represent things like, see here, a measurement taken on two different times, that is pre-test and post-test, with an intervention administered between the two time points. A measurement taken under two different conditions, that is completing a test under a control condition and an experimental condition. Measurement taken from two halves of or sides of the subject or experimental unit, that is measuring hearing loss in a subject left and right ear. You can perform that also, pair t test, taking observation on the hearing level or hearing loss on the left ear and on the right ear. The purpose of the test is to determine whether there is statistical evidence that the mean difference between paired observation on a particular outcome is significantly different from zero. If they are significantly different from zero, it means they differ significantly. The paired samples t test is a parametric test, and this test is also known as dependent t test, paired t test, repeated measures t test. The variable used in this test is known as dependent variable or test variable, that is continuous, measured at two different times or for two related conditions or units. And these are the common usage, that is statistical difference between two time points, statistical difference between two conditions, statistical difference between two measurements, and statistical difference between two matched pair. And you can see the statistical difference between the a technique, you can say. Note, the paired sample t test can only compare the means for two and only two related, that is paired units, on a continuous outcome that is normally distributed. The paired sample t-test is not appropriate for analysis involving the following, that is unpaired data. There we will perform independent sample t-test. Comparisons between more than two unit or two groups. A continuous outcome that is not normally distributed, then we will go for the non-parametric test. And if we have an ordinal or rank data, then there we will go for the non-parametric test as well. To compare unpaired means between two groups on a continuous outcome that is normally distributed, choose the independent samples t-test, as we know. To compare unpaired means between more than two groups, we will go for the ANOVA, one-way ANOVA. To compare paired means for continuous data that are not normally distributed, then we will go for the non-parametric test. And the equivalent, equivalent non-parametric test, which is equivalent to this paired t-test, is Wilcoxon signed rank test. To compare paired means for ranked data, choose the non-parametric Wilcoxon signed rank test, as it has been said in the previous slide. So these are the data requirement. They are same. The observation must be, the variable must be continuous, observations must be independent, and two times observation must be taken on the same group, and the observations must be sample must be random, that is observations should be independently distributed, and they must be normally distributed. It means they must come from the normal distribution, and there must be no outliers in the data, otherwise p value will be affected. There is two notes in this slide. We'll see, when testing assumptions related to normality and outliers, you must use a variable that represents the difference between the paired values, not the original variable themselves. If the non-normality and outliers are there, when one or more of the assumptions for the paired t-test are not met, you may want to run the non-parametric, that and the equivalent non-parametric is Wilcoxon signed rank test. Even if you are having observations less than 6, then we will perform Wilcoxon signed rank test whether there is normality in the data. The hypothesis can be expressed in two different ways. See here, either mu1 is equal to mu2, that is mean before and after is equal, and it is not equal, that is two-tailed test. Or you can see put it this way, mu1 minus mu2 is equal to 0, and mu1 minus mu2 is not equal to 0, where mu1 is the mean of the first measurement, and mu2 at the second measurement. See here, the test statistic for the paired samples t-test denoted t follow the same formula as the one sample t-test. See here, only this is taken as the difference. This is mean of the difference. Sometimes we denote it by d. So it is d bar upon sd. And this is 0. Actually, we are taking just the difference is 0. So this is the standard error of this statistics, x difference bar. So this is sample mean of the difference, and this is sample size, and this is standard deviation of the difference, and this is standard error of the this. Actually here it must be x bar difference, and the degree of freedom is n minus 1, as this 1 degree of freedom is left here, the constants. And anyone has any problem?
Please continue.
The calculated, we will see, we'll calculate the t value, and we accordingly we can see the tabulated value also, which is known as critical value from the table, and there is no need to see that value, because all the softwares are giving the significance level through p value. So we will see the p value, and obviously data setup is that you must have continuous numeric variable, and we'll set them in two columns, and we'll perform that test. And to perform that, we'll go to analyze in SPSS, analyze, compare means, and go to pair t-test. And this way you go to compare means and here pair t-test, and then this dialog box will be opened. You just click on one, and by this arrow this will be placed on variable one, and the another one on the another variable. Otherwise you can drag and drop, and just click on OK. You will get the analysis. So here you can see, before performing the test, as we have discussed, we should see whether data is normally distributed or not. So you can check for the tests, as well as you can see it through the box plot. And so this way we'll run through analyze, compare, mean, and pair t-test, and you will see these tables after the analysis. This is paired sample statistic and paired sample correlation. So you can see here, this is just checking the average marks of the English as well as math equality of the class. So see here, there are 398 persons in the class, and the average marks for the mean is 82.7, and for math is 65.4. And standard deviations are this for the population, and standard error for the this sample mean is these for the English as well as for the mathematics. And here you can see the correlation is 0.243. It means there is a very weak correlation, and you can see here that both the variables are uh, uncorrelated actually, but there must be correlation actually. So see here, this is paired t sample t test. You see here the difference, English minus mathematics, not mathematics minus English. Accordingly you can set. So the mean of this difference is this, and standard deviation is this, and you can see standard error is this for this sampling distribution of this mean difference. And you can see the t value is this, and degree of freedom, as we have discussed, 398 minus 1, that is 397. And two tail test, the p value is less than 0.05. Since p value is less than 0.05, it means there is a significant difference between the average marks of the two subjects. And we can see here from this table that there is a big difference. It is 82 and this is 65. That is why, and the test is also saying that one, that the difference between the two is significant, because p value is very less than 0.05. You can see here, this is tabulated value. Actually it is given tabulated value, and calculated value is this. See here, 36.316, and this has been taken from the table. This is 36.313. Actually this is calculated value, and the tabulated value is this, where it is tabulated value. So on the every English, no, it has not been calculated from the table. We'll see only through the p value in this table in software. Otherwise you can calculate here. This p value has been calculated by the software. Otherwise you can see this tabulated value, which is also known as the critical value. You just see the t table, and you see the value of the statistic at 5% level of significance, and at 397 degrees of freedom. So you can compare, and you will see that that value will be less than 36, because whenever calculated value is greater than tabulated, we reject the hypothesis, and we are rejecting that one. So that value will be less than 36. Now moving to one-way ANOVA. Now if we wish to perform the test for the equality of more than two means, independent samples, if you are dealing with the equality, if you wish to test the equality of two means, it means if you have taken two independent samples and you wish to know the whether the population mean of the two populations are same, then we perform independent sample t test. Now if you are dealing with the more than two samples, Then if you wish to know the equality of several means, it means more than two means, then we perform this, I mean, ANOVA test. And in ANOVA it is, as name suggests, that this is analysis of variance. That is, the whole variance of the data is divided basically in two sources, that is two parts. That is why it is known as this is partitioning of the variance. And one variation is supposed to come from the assignable, due to assignable causes, and due to random, one is due to random causes. And on the random causes, we we do not have control on the variation on the random causes, that is there, which is also known as natural variation. So say uh, random variation, say disasters are considered in the in natural variation or in um, random variations. You cannot control them. So these are out of the hands. They are not in control. They are not controlled by the human hands. That is why we suppose them that this is God's will, and the rest one is due to assignable causes, and we say them that they are our own will. So I am not going into the deep. There we use different regression models, and then we perform, we see how many sources are coming from I mean, this assignable variation is coming from how many sources. It means how many sources are responsible for the assignable variation. If there is only one source which caused the assignable variance, then it is one way ANOVA. If there are two sources of variation, then it is two way ANOVA, and so on. So here we see, uh, I would like to just share one example. Suppose some students are taking admission in the university, and they did their 10 plus 2 from different colleges. So some of the students are coming from the same colleges, and same colleges, and some of the students are coming from the different colleges. So now a test is performed, entrance test is performed, and you can see the variation among the units, among the students, numbers of the students. And there are two type of variation you can observe: one between the schools, and another one among the schools. Sorry, ek within the school, and one another one is between the or among the schools. So one is very interesting. One is here, one is due to assignable causes, and another one is due to random causes. So just think about which one is due to random causes, and which one is due to assignable causes. See here, the variation on which we have no control. It is not controlled. It is not in the human hands. So that type of variation is known as random causes of variation or natural variation. And we can see a variation within the school is not, will not be eliminated by anyone. This variation is natural. If we are teaching a class, then there is a difference in the marks of the students of the same class, while I or you are just taking the class. But between the schools it may be reduced, because it may be some lack of the facilities in different schools, lack of good teachers, lack of good laboratories, lack of some other facilities. These facilities may be provided to the schools, but how can you make all the students get same marks? So that is natural variation, and that is, so there is only one source of variation, because we do not take into consideration the random causes of variation. So there is only one source, that is between the school, which is causing variation in the marks of the entrance test.
Sir, can we take break 5 minutes?
Definitely.
Okay. So we will take 5 minutes break, and after that we will continue.
Sure.
We can continue, sir.
Definitely. So this is actually just an extension of the independent sample t-test. So there the F statistic is used, and we calculate different sources of mean sum of squares due to different sources, and we perform the variance ratio. So since we are taking the ratios of the variances following the chi-square distributions divided by their respective degrees of freedom, so this follow the F distribution actually. So these are the common usage of one-way ANOVA in field studies. Seldom, very less times it is used in field studies, but it is very much used in experiments, laboratories, and cost experiments. So one-way ANOVA is commonly used test for the following: statistical difference among the means of the two or more groups, statistical difference among the means of two or more interventions, and statistical difference among the means of two or more change scores, as we have discussed for the T statistic as well for the two groups only. Both the one-way ANOVA and the independent sample t-test can compare the means for two groups. However, only the one-way ANOVA can compare the means across the three or more groups. So it means independent sample t-test is a special case of this one-way ANOVA, and we can say one-way ANOVA is an extension of this independent sample t-test. If the grouping variables has only two groups, then the results of the one-way ANOVA and the independent sample t-test will be equivalent. In fact, if you run both the independent sample t-test and one-way ANOVA in this situation, you should be able to perform confirm that t square. We know that t square follow F distribution. Data requirement is same as in the case of say independent sample t-test. The variable must be continuous, independent variables must be categorical, observations must be independent, and there should be no outliers, and the parent population should be normally distributed. This, and there must be one thing, there must be homogeneity among the variances, and actually this is known as a space in case of more than two variables, we will see the sphericity of the we will consider just like sphere, so sphericity of the variances. So not this homogeneity term will be used there, we will use their sphericity, and this will be tested through yes, one more thing. If the null hypothesis in case of one-way ANOVA will be rejected, then we will perform the postdoc test, also known as the multiple comparison test. There you can test this Dunet test and Tucky test, and there are so many tests we will see in spaces. When the normality, homogeneity of the variances or outlier assumption for the one-way ANOVA are not met, you may want to run the non-parametric test, and the equivalent non-parametric test to one-way ANOVA is Kruskal-Wallis test. So researchers often follow several rules of thumb for one-way ANOVA. See here, each group should have at least 6 subjects. We have discussed, if you have ideally more, if you have less than 6 or lesser, then we prefer to choose non-parametric test, and that is Kruskal-Wallis test. And there must be balanced design. If you are not dealing with the balanced design, if there is huge difference among the sizes of the different groups, then p value will be affected. So it is better to use the not very much balanced, but somehow balanced groups. So this is null hypothesis that mu1 is equal to mu2 is equal to mu3 and equal to so on mu k. That is if you are dealing with the if you wish to test the equality of k means, and alternative will be that at least one is not equal to another one, and these are the population means different. This is actually one-way theoretical one-way ANOVA table. These are the sum of square due to treatment, sum of square due to error, and total sum of square. And these are the corresponding degrees of freedom. And when we divide these sum of squares by their respective degrees of freedom, we get the mean sum of square, and the ratio of these two is the variance ratio, and that follow the F statistic, F distribution. So these are different sum of squares, and this is actually variance ratio. We can see these are the degrees of freedom for error as well as for, you can see here, this is for the treatment. If you are dealing with the T treatment, this is T minus 1, and this is RT minus 1, and this is RT minus 1 total, R minus 1 T minus 1. This will be R minus 1 T minus 1, and this will be RT minus 1 if you are dealing with the repeated, if you are dealing with the comparison of T treatments and every treatment is repeated R times. It means we are having R observations on every treatment. Balanced design. The data setup, we know that the dependent variable must be quantitative and independent variable must be categorical. To run the ANOVA, we know we'll go to compare means, and we'll go to one-way ANOVA. See here, analyze, compare means, and we'll go to one-way ANOVA. This dialog box will be opened there. You just put dependent variable here, and the whole independent factor, that is, you are dealing with the more than one independent group, so you put here the categorical variable, and you go to postdoc test if you wish to perform, and then click OK. You will get the data. See here, if you are going for the postdoc test, then see here, you can perform so many Bonferroni test, Tucky test, and you can select here Dunet's T3 test. So you can perform any of the tests. You can see here Dunet test. This is a running procedure. We go to analyze, compare means, and one-way ANOVA. This will be and the output of the SPSS. You see here, these are the sum of square, these are the degree of freedom, and these are the mean sum of square, and the ratio of the two is this, and this value is the p value for this statistic, that is equal for the equality of several means. So it is point in this example which has been considered into the slide. You can see here it is less than 0.05, so we will reject the null hypothesis. This is the plot for performing the say two, for two groups. Definitely conclusion will be taken on the basis of the p value. If it is less than 0.05, then we'll reject the null hypothesis. Now repeated measure ANOVA is nothing but it is the extension of the paired t-test. If suppose if you wish to know that say some you are treating some say psycho patients, and you have a group of psycho patients, and you are giving a particular drug to them, and you are checking their wellness after every week or after every month, then you take the observations, and you will have repeated measures, so more than 2 times. If you are having repeated measures only 2 times, then it is paired t-test, and if you are having repeated observation more than 2 times, then it is repeated measure ANOVA. Or you can say if you are some giving diet plan to a group to reduce their weight, and you are taking their weight in after every month, and if you are considering more than 2 observations, then this is a case of repeated measure ANOVA. So you have to just this is just extension of the t-test, pair t-test. So you just click on the analyze and go to general linear model and repeated measure ANOVA, and accordingly you put all the observations, and you will get the see here, these are the observations, say at these are the ID 20%, and this is first time observation, second time observation, and third time observation, and you can perform Here you have to just within subject factor name, you just say diet, and how many levels, say 3, and give the major name, and you just define and go to this, and you have to put all, either you select one by one or you select all and put them at once. Here all variables will be displayed, and you can go for different plots and for the model. Then you click on OK, and you will get the this way. You see here all variables are put here, and you can go for the option. Then in option you can calculate the descriptive statistic, you can calculate the estimates of the effect size, you can see the transformation matrix, and you can see different things. Click on continue, and click on continue, then go on factor. You see it is in, say, any name within factor which you have given name, that is diet, say, and see the number of levels, that is 3, and you can see. So you have to overall put here, and compare main effects, and you for performing this you can go for Barnfrand test, and click continue. You will get the this descriptive statistics, as we have discussed. Put tick on the descriptive statistics, and this is assumption of sphericity. It means this is nothing but this is just homogeneity of the variances for more than two groups. So a requirement that must be met before you can trust the p-value generated by the standard repeated measurement ANOVA measures ANOVA is the homogeneity of variances for of differences or sphericity assumption. For our purposes, it does not matter too much what this means. We just need to know how to figure out whether the requirement has been satisfied or not, because as we have seen in the case of independent sample t-test, that it gives the case with the equal variance or not equal variance, it provides the value of t. So similarly we'll see the by the same way we'll see the values of the statistics. And statistics in SPSS, to check the assumption of sphericity, we use the Mochle's test. You can see here this test for the sphericity. You see here the significance value is 0.494. It means it is much greater than 0.05. It means the data is homogeneous. Variances are homogeneous for all the groups. You can see here. This is actually a test within the subject. You can see here through different sphericity assumed and greenhouse glacier test, where we sphericity assumed, and these are the for these are tests for these are different tests for to check that sphericity. You can see here this is very much less than 0.05. So this is due to this test it is significant. So you can see here check the sphericity by different values, but in SPSS much less test is used for the same to test the sphericity of the whether it is if you are having homogeneity, it is good. If it is not having, then you can go for the analysis, and you will see very carefully. You have to see the value of the statistic. This is pairwise comparison. There's a multiple comparison test. You can see the different pairwise. This is comparison between when null hypothesis is rejected, then pairwise or multiple comparison test is applied, and you can see here this is comparison between first group and second, first and third. This is second and first, and second and third. This is third and first, and third and second. And you can see which is cause of the significant difference for the test, that is by which pair the whole hypothesis is rejected. which pair of treatment is significant for the difference among the groups. So this is a report. You can see here this tabulated value, calculated value is this, and you can see the p value is 0.006, which is less than 0.05. So we can reject the null hypothesis. And this is all about the references. This I mean, and this material has been taken from this website, and you can have more and more information from this site. And if you have any query, any question, then you can ask. But before asking any question, we should see the performance on the SPSS. Then we will consider the or you can ask first. First,
Yeah,
you
sir,
see.
we will take some questions.
Definitely.
And please, sir, stop sharing your screen.
You ask the question, then we'll perform the test on SPSS.
Yes,
different
yes.
tests.
We will take some questions from the participants. Okay. I have just now interesting participants can ask the question. Please unmute yourself.
Sir, can I ask a question, please?
Yes, please.
Definitely.
Hello.
Sir,
Yeah,
you
one
have
by
given
one, please.
One example wherein you have quoted that English and mathematics difference, but they
Yes.
are two different subsets of population: English score and mathematics score. How can it be an example of paired t-test? Is it different?
That must not be pair t-test, but this had been taken. Actually, that repetition is that sample. It is considered this way that we have that is not actually a very perfect and I mean example, but the group is same. That is the sense behind taking that example is that the group is same. If you are taking performance, if you are taking the observation on the same group 2 times, then there you can perform t-test, pair t-test.
Was it an example of difference or differences?
Difference?
Of differences.
This is example of
Is
differences.
it the example of difference of differences? Because difference between two things, and again he was checking the difference of same two things.
No, it is the actually we are checking the score of the differences, and that score will be taken if you are considering the difference as a variable. Then the mean score, the test value will be 0. Otherwise, you can check the equality of the means of the two.
Hello, can I ask a question, please?
Yes.
Yeah.
Suppose we are having 3 groups, and instead of doing ANOVA, we do the unpaired t-test. We compare A with B, B with C, and A with C. Will there be the statistically it will be wrong, or
No,
it will be
No,
good?
it is good. It is good. No problem.
But it will take some time. It will be complicated. That's why ANOVA is doing.
Okay,
No,
I
no,
heard
sir.
one of the statisticians, he said that no, the result will be different. There will be error in the study. ANOVA gives a less error if we compare. And
Definitely, that is why all groups are taken together. That will be good if your null hypothesis is rejected. But if
because
you are,
in many
it
of
is
the
accepting.
cases I have seen many students, they are doing this. If they are having 3 groups instead of ANOVA, many of them are doing, they're comparing using the unpaired t-test. So is it correct, or it will give a different result? That's what I wanted to know. The result will be same.
wrong.
Result must not be different, I think.
No, sir, it is
If you
wrong
are
because
using
the
very
alpha error
carefully.
increases in that case.
Okay. Thank you.
Good evening, sir. My question is, can you elaborate again on the post hoc test and give the example in which conditions it is to be used?
Ma'am, if you are suppose you are testing the equality of 3 groups, and your hypothesis is rejected, and the alternative hypothesis is suppose that there is different one at least one mean is different from the other means. So you have to perform pairwise test. So first group will be tested with second, and first will be third with two, and second will be third. So there will be three combinations, and we will see due to which this difference is occurring, which is due to which the whole result is significant. So there we will perform ad hoc postdoc test, and postdoc test means that is, I mean, this t test, independent sample t test.
So is
Good
this
evening, sir.
MANOVA same as the multiple ANOVA, repeat ANOVA? MANOVA and repeat ANOVA?
Repeated ANOVA is the extension of pair t test, ma'am,
Then
where
what is
we
MANOVA? MANOVA.
multivariate ANOVA, that is if you are dealing with more than one variables at a time, dependent variable,
Okay.
that
Okay,
is
fine.
MANOVA.
Excuse me, sir. Sir, I have a question. If we have two samples, one with the sample size below 30 and another with the sample size above 30, can we perform an independent two sample t-test, or we have to go by any assumption? And is there an assumption for that?
You can go for the t test, no problem. Otherwise, if
Okay,
you
the
are
sample size
just
30, above 30 and below 30 will not make any difference.
no, if you are it will, ma'am, it will depend. We have discussed in the lecture that if the size is very much different, if there is huge difference between the sizes of the two samples, then it will make the p value, I mean, ineffective. Otherwise, if you are say taking 25 and another one 35, it hardly makes the difference.
So at what what is the level like at which we can think like the difference is very large, because it can be
Definitely.
55, it can be 25, 30, 55, it can be 25, 65. So at what point we
So
can decide?
there you can say, you should first, you should perform the Levene's test whether there is homogeneity or not. If it is homogeneous, then you can go for the test. Otherwise, you should go with the non-parametric test.
Okay, thank you.
Sir, post hoc test, is it something data dredging?
Pardon?
Is post hoc test,
Yeah.
does it amount to data dredging?
Mm, I don't think so, because postdoc tests are performed there when we have a complete test for the when the hypothesis is rejected. So there we have no choice to, we have no test to perform that. So we are I mean bound to perform the traditional say t test. If you are saying if your ANOVA, say one way ANOVA is rejected, null hypothesis, so what is left? We are bound to use t statistics. So pairwise we will use, and that is done in postdoc test. Pairwise, there we consider.
Right, sir.
So I think there is no more questions. So we will continue for
I
the.
think
Yeah.
quickly we should see the analysis.
So
Yes.
time is
On
very
SPSS.
short now.
Yeah.
Yeah,
Please.
definitely, sir. This is data for the one sample t test, and very quickly I will be sharing the whole description as well as the data with you all. So this is data for performance of the 10 different air conditions, ACs, and the guarantee, it is we are just testing that the average I mean performance of AC is 5,000 days. So the test value will be 5,000. So to quickly we'll see how to analyze it. we'll go to analyze and compare means, and then we'll go for the one sample t-test. And there you can say days is your main variable. You can put it into the test variable, and here see the test value. So here we have to put 5000, and then you can go for the option. Okay, 95% confidence interval, no problem, and you just click on OK. You can see here the average of the average say life of the 10 ACs is 4880 days, and the standard deviation is of 350 days, 53 days, and the standard error of the this mean is 111 mother triple one. And see here the value of the t statistic is this, and degree of freedom is n minus 1, that is 10 minus 1 9. And here we can see the p value. P value is 0.311. It means it is greater than 0.05. So if it is greater than 0.05, then we'll accept, we'll not reject the null hypothesis. It means we can say that the average performance of the or average life of a AC is 5000 days. Now to perform the independent sample t-test, we are having the same example which we considered yesterday, that there is a two group of teachers, that is male and female. We are having 20 male and 20 female teachers, and we are just we wish to check whether the average salary of the male is equal to the average salary of the female. So to perform it, we will go to analyze, compare means, and we'll go to independent sample t-test. And see here, your salary is the main variable, and your grouping variable is this gender. And you just click on define group. You have to define group. So before going to it, I would like to see, you see here, you click on this. We have given code 1 to say male candidates, and 2 to female candidate. You see here, 1 for male and 2 for female. So we'll accordingly use that one. Analyze, compare means, and go to independent sample t-test. Salary as the main variable, gender as the grouping variable, and define group 1 for male and 2 for female. Automatically it will take, and you go for the option 95% confidence interval, no problem, and click on OK. You will see here this is a group statistic. You can see 20 male, 20 female, and the average of the male is 49,900, and for the female is 39,400. And these are the standard deviation, and these are the standard error for these means. And you can see here automatically Levene's test is applied for the equality of variances, that is homogeneity of variances for the two populations, male and female. You can see here equal variances assumed and equal variances not assumed. So the value of p value for this Levene's test is 0.435, which is greater than 0.05. It means there is homogeneity of variance among the two groups, male and female. So we will go with the first one. So we'll see the test value is 4.088, although it is same for both the situations. And the degree of freedom, see here, equal variances not assumed, it is calculated through that formula. So it has come in fraction, and it is n1 plus n2 minus 2. So 20 plus 20 minus 2 means 40 minus 2, that is 38. And see here the value of the t is 0.000. It means it is very much less than 0.05. So we will reject the null hypothesis. It means the average salary of, it means average salary of male is not equal to the average salary of the female. Similarly, you can perform various this test in various fields of application. Now, for the pair t-test, see here, these are the observations, say something before performing that test, and something after performing the test. You can see here description of the pair t-test. This is actually a case study. ABC University arranged a specific faculty development program for one segment of its teachers. The university wants to measure the change in the attitude of its teacher after the FDP. For this purpose, it has used a well-designed questionnaire which consists of 10 questions on the 1 to 5 rating. 1 means strongly disagree and 5 strongly agree. The university selected a random sample of 20 teachers. So this way, this has been performed, and you can see the scores. And this is before FDP, and this score is after FDP. So you can see whether the FDP is going to be effective or not. So we'll go to analyze, compare means, and paired sample t-test. So before one and after in another, and we'll go for the option 95% confidence interval and click on OK. You will have, you can see here. You can see here, this is descriptive paired sample statistic. These are the means and number of observation, standard deviation, and standard error. You can see here the correlation, the very weak correlation. But this value is 0.0, more than 0.05. It means the observations are it means they are having very weak correlation. It means almost independent. See here, the t value is this, and the p value is less than 0.05. Since the p value is less than 0.05, it means we will reject the null hypothesis. It means the FDP is effective. It means there is a change in the behavior or whatever we are testing after FDP, attitude, in the attitude. Sorry. Now quickly we'll go to perform ANOVA. This is actually promotion of a product, and this is the sale of a product which is highly promoted, and these are the sales with medium promotion and low promotion. So these three we wish to know whether this promotion of the product is going to be effective or not. We see the average sale of high promoted product, medium promoted product, and low promoted product are same or not. So we'll go for the analyze. Since we are we can see here, we will code them: high with 1, medium with 2, and low with 3. You can see here, 1 is for the high promotion, 2 is for the medium, and 3 is for the low promotion. Then we'll go to analyze and compare means, and we'll go to one way ANOVA. So you can see here, per day sale is the main variable, and this is the factor, and there is no need to define different groups, because when you are performing independent sample t-test, there you need to perform define two groups, because if you are dealing with say several groups, then it will take very much time to define different groups here. So SPSS take care of it. So you can go for postdoc test, even you can go for the Tucky test, you can go for the DUNet test, and click on continue. You can go for the options. You can have descriptive and homogeneity of variance as well. So click on continue and click OK. So see here homogeneity of variance. This is homogeneity. There is homogeneity in the variance by the Levene test because the value of the p value is greater than 0.05. It is 0.2, and you can see here this is ANOVA, and you can see here the value is p value is less than 0.05. So your hypothesis is rejected here. It means this promotion is having effect on the sale of the product, per day sale. So now we'll go for the postdoc test, that is multiple comparison, which is going to be more effective. So everyone is effective. See here, through Tucky test and Dunit test, through both the test, we can see the significant level is 0.05. Yes, mean everyone is low is significant in comparison to medium, medium is comparison to effective in comparison to high, and obviously low is sensitive or significant in comparison to high. You can see here this way. Now the last one, that is repeated measure ANOVA. This is diet example for the diet to see the these are the say weights of the 15 persons, and after 1 month you are applying some diet chart. You are giving them some diet chart. They are on diet. So whether your diet technique or your diet chart is going to be effective or not, to see the observations are taken 4 times, when on the first day, and then after 1 month, then after second in after 2 months, and after 3 months. So we'll see whether the technique is going to be effective or not. So we'll go to analyze, and we'll go here not to compare mean, we'll go to general linear model, and we'll go for the repeated measure, and we'll define the factor, that is level is R4, add, and factor name say diet, add, and we'll define. You can select all and put here. You can go for the model full factor, no problem. Continue. Contrast, polynomial, you can go for the repeated, change, continue, no problem. Factor, it will be given in different way. Okay, save. You can save, and you can save the different values, say standardized predicted values and unstandardized residuals, and then click on continue, and option you can go. You can check overall factors here, and you can go for the descriptive statistics. You can go for the homogeneity test, and say residual plot, and then click on OK, and then click OK. See here, this is warning that homogeneity specification in the print sub command will be ignored because there are no between subject factors. So see here, within subject factors, and this is descriptive statistics for the different factors for base weight, baseline weight, and after 1 month, 2 month, and 3 month. And you can see here multivariate test, multivariate hypothesis. You can see here that you can perform the multivariate test as well, ANOVA. And see here much less test for specificity. You can see here the value is 0.005, less than it is less than 0.05. So there is not I mean homogeneity in the variances for the all 3 groups. So we can see through the data that at first month it was very high, and at 4th month it is very low. So this is the variation is not homogeneous. Actually, variation is not homogeneous, not equal for all the groups, for all the observations in every month, as the test is saying. And you can see this is significant for all the factor 1 and error factors, and test for within subject contrast, you can see all are significant. So you can see for factor for you can see that level 1 and level 2 are significant, you can level uh, 2 and level 3 are significant, and level 3 and level 4 are significant. You can see here that every level has difference. So every it means this diet is going to be effective every for every repeated measures. And you can see here between subject effect, it means the main ANOVA table is this. You can see here the diet is going to be effective because the p value is less than 0.05, and you can see the different residual plots which we have taken into consideration. So this way you can go for the repeated measure ANOVA. I think this is all about today's discussion, and tomorrow we will be discussing the, I think, regression analysis, bivariate as well as multivariate. So still, if you have any confusion, any question, then you can ask, please.
Hello. Hello, sir.
Yeah.
Hello.
Hello. One by one,
Hello,
please.
sir.
Yeah. One by one,
Sir,
please.
I have one doubt, sir.
Yeah.
Hello.
Yeah. Sure.
Sir, in parity test, we compare the score between two groups. Okay. But hello,
Yes,
sir.
yes, please
Sir,
ask.
Sir, but score data. Wait, if you have data in the form of score or rank, so we compare by using the Wilcoxon sign rank test. No?
definitely qualitative. In most of the qualitative data is there, then we go for the non-parametric test, which will be we will be discussing I think day after tomorrow.
Hello, sir.
Yeah.
Sir, in that repeated ANOVA, why we cannot go for post hoc test?
Why we go we when your hypothesis is rejected, we go for the postdoc test, and there we use pair t test. We are bound to use that one. We have to see the pairwise. We have just seen that pairwise. We have seen all are significant because the hypothesis was rejected actually. So we do that. Hello.
Yes, sir. Any other question from the participants? You may please ask.
Yes, sir.
Yes.
Sir, from where has this number of 30 come for? Like you mentioned that at least 30 subjects are mandatory for these tests to be valid. But in the examples that I saw, that there were 15 subjects or even 20 subjects. What will happen? What will happen if the subjects are less, and what will happen if the number of subjects are more than 30?
Actually, if you see what is left, we have not seen actually. We just it was skipped through mind that we should check first normality of the data. If it is normal, then you can go with the parametric test. So it is better if you can see the normality. Generally in practice, what has been seen that if you are taking the observations more than 30, there is a clear picture of normality. That is why a small sample has been taken up to 30. So
if more than 30, sir, then also it's okay. But if less than 30, then we definitely have to check for the normalcy first, right?
Definitely we should check for the normalcy, and then if it is not normal, then we should go with the non-parametric test.
Okay, sir. And if the sample size is much more than 30, like if it's 100, let's say, then what will happen,
Then
sir?
then there must be normality. It is suppose that the data will be normal. Even then you perform the normality test and see.
The thing that you mentioned in the beginning, sir, the Z test, which is for more than 30
Yeah,
sample size.
definitely.
So we'll
We
be
will go for
knowing
the
about that.
yeah, same statistic is used almost the T statistic and same type of statistics are used for the Z statistic. So,
One
but for the large samples.
Yes, sir. One more thing, sir.
Yeah.
30 is the number of subjects that are required, or 30 observations in total are required for this
Independent
test to be.
observation, that is subjects, the 30 subjects say we are taking one
Subjects are required.
that is
So
sample.
if we are doing ANOVA in, let's say, four variables, four group of data, then we'll have, if 30 subjects, then we'll have 120 observations. So this is what is required.
No, ma'am. If you are performing ANOVA, then there is a requirement of say more than 30 in each group. Say
In each group. So that is what, if four groups are there, then 30 plus 30 plus 30 plus 30, that is
definitely,
120.
definitely.
Okay,
At
okay,
least.
okay.
Otherwise, you may take different sizes of the groups. You can also
Yes, sir.
take.
Okay, okay. Thank you, sir.
Sir, my one small suggestion,
Yeah.
this sample size does not came into picture for the parametric as well as non-parametric test. So normally, if the basic assumptions are violated, then we may going for the non-parametric methods. So
Sir,
here,
definitely, sir. If you are performing the, I mean, exact sampling distribution, that is TF and chi-square,
yeah,
there is a assumption that sample size should be small.
small.
There is a assumption.
Okay. If it is more than 30, we are going for the large sample sets.
Definitely, we will perform Z test, that is normal distribution test.
Oh, okay. If you collect some observations, suppose more than 100 observation, any survey method. So if it doesn't follow normality assumption, definitely we may going for the non-parametric method.
Definitely, it should go. Definitely.
So, so the sample size does not came into picture for the parametric as well as non-parametric method. So depends upon the scope and for study objective. If you violate the assumption, then you may going for non-parametric test.
Definitely, sir. One of the assumption, if you are performing say T test, then if you are suppose you are having very less observations, then you are bound to perform some non-parametric test, or if there is no normality, and if there is normality, then you should, if the sample size is less than 30, then we should go for the TF chi-square, whichever is required.
Okay, another thing is, if while performing ANOVA, not necessary that the individual group must be 30, more than 30. Even if it's less than 30, we can perform ANOVA.
Then we'll go, definitely we can perform. Then there we have to check the normality, sir. If there is not normality, then we'll go for the Kruskal-Wallis test.
Yes, yes.
Equivalent non-parametric test.
Yes, it's correct, sir. While performing ANOVA, we have to test for the homogeneity of variances, sir.
Definitely.
Understood.
Definitely.
If it is okay, then we are going for the ANOVA procedure.
Yeah.
Not necessary that in the ANOVA, each group must consist of more than 30 observations. Even it might have less than 30 also.
It is actually, I think it is said that to make this spatiality assumption. So otherwise, if you are just taking a very huge difference among the groups or sizes of the groups, then I think the test will not perform very well, parametric.
So normally, sir, usually in any goodness of it, the sample size is sufficiently large.
Definitely.
Then you discuss tomorrow about the multiple regression.
Yeah.
Then R and R square, adjusted R square must be equal. So N is sufficiently large. So that will come into picture. Normally, if the parametric assumption is violated, we may going for the non-parametric ANOVA, and the test, as you suggested earlier, any test can be administered.
Definitely, but I am just saying, sir, that sample size is also one of the assumption for the, I mean, these parametric tests.
Okay, sir.
Sir, we can discuss
Thank
later.
you, sir.
Later,
Thank you for
later.
your
Thank you,
suggestion.
thank you, sir.
Thank you so much for your valuable suggestions. And if any other question, then we'll continue. Otherwise, we will take some questions in the
Yes.
tomorrow's session.
Hello, sir. One small question. Is subject and
Hello.
sample are same meaning?
Pardon, your voice is not coming clear.
Hello, sir.
Yeah.
Yes, please.
Is subject and sample has the same meaning?
No, sample is the collection of observation on the subjects.
Okay.
Group of subjects is sample.
Okay.
Good evening, sir. Am I audible?
Yes,
Yeah.
ma'am. Please.
Sir, actually, you mentioned, like I had a doubt that we can do either independent t-test or one-way ANOVA when we are just comparing like between two groups, right? Means suppose we did a study on diabetics and controls. So we can do independent t-test or one-way ANOVA, right? Anyone.
Yeah.
So sir, like because in some articles they do this, some articles they do ANOVA. So what would be better, like, you know, to
T-test is better, ma'am, if you are dealing with the two groups only.
Okay. And sir, like वो जो t value आती है, the t value that we have as we saw in the results, minus or plus, or it has a value. Does that have any like, you know, importance?
हाँ बिल्कुल मैम, बिल्कुल बहुत इम्पोर्टेंट है. It is very important, but in the sense of this, I mean software, because p value is there, so that is not important. But if you are if you are taking decision on the basis of the calculated value and on the basis of the tabulated value, that is also known as critical value. So you have to see the critical value from the table, and there you can compare that one. So it is already compared in software, and software is giving output in terms of the p value.
P value. Like sir, suppose we did a study and we have a value for some things, like for blood glucose, for diabetics, and for controls. We did this test, and now we get a t value, and we got a like p value was significant. Okay. And in that case, will that t value, like obviously while publishing, while putting it in the paper, we put the t value. So does that have any, I mean, we have to explain it, or just jo bhi aaya we have to write it?
हाँ, उससे कोई फर्क नहीं पड़ता मैम. उससे कोई फर्क नहीं पड़ता, वो तो ऑब्जर्वेशंस के ऊपर डिपेंड करेगा ना. That will depend on the I mean observations values.
No, actually जब वो माइनस में आता है तो I get worried कि कुछ प्रॉब्लम है.
नहीं, उससे कोई फर्क नहीं पड़ेगा मैम.
तो जैसा है सर उसको फिर लिख सकते हैं.
हाँ, लिख सकते हैं, definitely.
As long as it is significant.
Definitely.
Okay, thank you sir. Thank you.
Okay, sir.
Okay.
So, thank you so much, sir, for your valuable suggestions,
Thank you, Elangavan sir. Very much thank you.
So, actually, he is a very senior professor of statistics, and I think he is head of the department.
We are learning a lot from you, sir.
Okay.
Head of the department, I think, sir, you are head.
Yeah, heading the department now.
In
very nice, sir.
Annamalai University, sir.
Annamalai.
Yeah. How are you?
We have hands-on training SPS also. So
very nice, sir. Very nice.
Yeah. Thank you so much, sir. And thanks
sir,
to all.
My sincere suggestion is giving
Yes.
more focus on practical.
Yes,
so definitely, sir. Definitely.
For the participants.
Next time,
because
definitely.
Today, we are spending only 20 minutes only.
Actually, sir, we are statisticians, so we try to explain whatever we are having inside of ourselves. It generally take very much time.
Yes.
So if I don't want actually to skip the steps. That is why it is.
Actually, this is the problem with the statistician, that we want to learn all the things to participants. If their concept is p-value, then we will describe the concept of p-value. If there is a t-test, then what is the story behind the t-test?
Yes.
This is the problem.
It's good, sir. Tomorrow, the regression is more important to the participant. You can
definitely, sir. Definitely, it is going to be very important.
Thank you. Thank you, all the participants. Thank you so much, sir.
Thank you, sir.
Thank you.
We will meet tomorrow.
Very nice. Definitely.
Sir, kindly post all the PPT. It would be useful.
Yes, sir. It will be sent to your mail, sir.
Mail, yes, it's better.
Yeah, it will be sent to your mail. in advance.
Okay.
I think these will be sent to your mail. Please check your inbox.
Okay. Okay.
It is sent in advance, sir.
Okay. Okay. Fine.
Thank you so much, sir.
So
Okay,
another one suggestion is finally
yes.
in the final day you put one validity session. You spend 10
Yes,
minutes. So
of
get
course,
the
sir.
feedback also.
Yes, of
Definitely,
course.
sir.
Thing is,
Definitely,
the
definitely.
Definitely, sir.
complete list of participants together through mail ID and other thing. It would be useful.
Yes,
Bilkul,
definitely, sir.
Yeah, for the participant. Okay, thank you.
Thank you so much.
Thank you, sir.
Thank you
Okay,
all.
bye bye. Good night. Good night.
Zoom.